Okay, well, I guess I could do the introduction here. Today we're very happy to have Leo McAllister, who's going to give us an update on finding de Sitter vacua and string theory. So take it away, Liam.
Thanks, Mark. Thanks a lot for the invitation. It's great to be able to see all of you. I'm excited to tell you about our work on finding de Sitter vacua. I was instructed to make this about 45 minutes with time for discussions at the end, and I'll try to do that, but I hope you'll also jump in and interrupt partway through. And my goal is to give a general overview of what we're trying to do and just enough details to fill in the picture. So this is based on work that came out in June. It's work with Jakob Moritz, Richard Nally, and Andreas Schaffner, and also building on some prior works. So the maximal goal of this work is to understand cosmology and quantum gravity, and to do so by finding solutions of string theory that actually describe our universe. This is too ambitious, of course, and our present goal, which is still, I would say, extremely ambitious, is to construct de Sitter vacua of string theory in totally explicit compactifications with quantified errors, and in so doing, to develop fully realized toy models of cosmology in four-dimensional quantum gravity. So the physics motivation for this, one of the key pieces, is the cosmological constant problem. And the real cosmological constant problem is too hard. It's certainly out of our reach, at least our reach right now. But we can access a sort of supersymmetric version of the cosmological constant problem. So we could consider, instead of finding a vacuum energy that's exponentially small and positive, what if we could try to understand vacuum energy that's exponentially small in magnitude but negative? So instead of finding a DS vacuum with small vacuum energy, we find a SUSY ADS vacuum with small magnitude vacuum energy. And what we'd like to do is see if we can explain how exponentially large supersymmetric universes can arise in a theory in which the fundamental length scale is very small. And what we'd further like to do is build on that understanding to use supersymmetric solutions as a foundation for constructing necessarily non-supersymmetric de Sitter vacua of string theory. And that's what we've done in some way. We've constructed candidate de Sitter vacua in totally explicit compactifications of string theory along lines laid out more than 20 years ago by Kachru, Kallosh, Linde, and Trivedi. What you're looking at here is a picture of the scalar potential in a compactification, that's the vertical axis, versus the Calabi-Yau volume in string units. And the pink curve has its minimum above 0. So this is a configuration that describes a metastable de Sitter vacuum. And the task is to explain how we've actually computed these curves and the extent to which you should trust the computation that led to this kind of picture. So there's going to be mostly overview, but some details, but I want to give you really at the beginning a picture of the assessment, like to what extent should you trust the claims we're making? How strong a claim am I really making? So what we do in our paper and in the associated GitHub files, we present in total detail the topological data of explicit compactifications, and we enumerate all the approximations that we've made in deriving the corresponding four-dimensional EFTs. And we then demonstrate that these EFTs have de Sitter vacua. What that means is that subject to our approximations, the compactifications likewise describe solutions of string theory that are de Sitter vacua. But the approximations are non-trivial. Some of them are straightforward, like weak string coupling, and as I'll show you, the string coupling is indeed really small in our models, but there are other approximations. And none of us involved in this work feel that all of the approximations are nailed down completely. We enumerate them, we list them, you can see what they are, but we haven't proven that they're all trustworthy. So I personally think that in time we're going to demonstrate control of the approximations, for example, by carrying out various computations to higher order, but this is not work that's complete. And for that reason, we call these solutions candidate de Sitter vacua. Okay, so summary of the talk, I'm going to describe our program of building vacua of string theory through computational geometry, and I'll explain how we've constructed, in flux compactifications on Calabi-Yau orientifolds, two kinds of things. First of all, supersymmetric ADS4 vacua with exponentially small vacuum energy. And then building off of those, candidate de Sitter vacua, at least at leading order in the G string and alpha prime expansions. Now, the methods that we use to get both of these things are the same, which is why I'm putting them both in one talk. It's really one kind of work. And ADS vacua are the foundation. They're now numerous and robust. We've made millions of these things. De Sitter candidates are rare, but we have found them. And so I'll tell you about both. As usual, it's easier to understand the supersymmetric thing first. Okay, so plan of the talk. First, I'll talk about the strategy and tools that one uses in general in trying to find vacua in compactifications. And then a little more specifically, our individual strategy for this kind of problem. Then, yes, question.
Hi, Liam. Sorry. So you're saying that it's actually leading order in G string and alpha prime. So does that mean that the higher order corrections could potentially make these de Sitter, like lead these de Sitter vacua autonomy back to ADS? Is that?
Oh, absolutely, absolutely right.
Okay,
Yeah.
okay.
Now I'm going to be much more specific about this later, but let me already address that point. That there are two pieces of the EFT: the supersymmetric EFT, and then the supersymmetry-breaking part, which is going to come from an anti-D3 brane.
Yes.
In the supersymmetric EFT, the control of the G-string corrections is excellent, as I'll show. And actually, we do go to all orders in alpha prime in a certain sense. In fact, all orders non-perturbatively in a certain sense that I'll describe. On the other hand, in the anti-brane action, we only work at leading order and alpha prime, and it's very, very plausible that corrections beyond leading order will destabilize these, and that's why further work is going to be required. That's the main reason for the word candidate in our title.
Okay, brilliant. Thank you so much. Okay.
So this item 2, yeah, thanks for asking. So this mechanism for a small superpotential, that's the physics engine of the work. We first have a computational piece, and then we have to have a physics idea for how to generate hierarchies. So that's part 2 of the talk, and then the third part I'll put them together and describe candidate de Sitter vacuum. So first, a bit about the strategy. So as a general reminder, a compactification of superstring theory to 4 dimensions that preserves minimal supersymmetry is characterized by superpotential, which is a function of some moduli fields, and a Kähler potential. And the superpotential is a holomorphic function. The Kähler potential is not a holomorphic function. Because the superpotential is protected by non-renormalization theorems, and because it's determined by topological data, it's knowable. With enough work, and I'll describe the work, you can come to have it in hand. And the Kähler potential is poorly understood beyond one loop. So if I were to write out the general structure, the superpotential has a tree piece and non-perturbative corrections. The Kähler potential has a tree-level piece, perturbative corrections and non-perturbative corrections. And what one knows in a favorable situation is the stuff indicated in red. So at the same time, the scalar potential is determined by both the superpotential and the Kähler potential. So ideally, you need to know both of them. And this is what calls for a bit of a strategy. Our strategy is going to be to use supersymmetry as much as possible for as long as possible, and to carefully choose a setting where the vacuum structure will end up being dominated by superpotential terms. And in particular, superpotential terms set by integer data, by topology and quantized flux choices. Moreover, we're going to do this in a setting where the number of vacua is practically unlimited, so if we don't like one, we can just go find another. And we're going to do this by developing computational geometry software that will allow us to obtain the superpotential systematically by combinatorial operations, so very quickly and in large numbers of examples. And finally, and this is the sort of basic physics idea, we're going to find cases where vacua result from competition among exponentials, not from competition among perturbative terms. So some work will be required to arrive at those situations. When we get to them, they'll be very beneficial. Okay, so that's the strategy. We're going to do this in type 2B string theory in flux compactifications on orientifolds of Calabi-Yau threefold hypersurfaces at weak string coupling. And I don't want to introduce like full notation for the various moduli fields in this setting and write out the EFT in great detail. Of course, we do that in the paper. Let me try and give the overview picture of this setting. What we're going to show is that the leading order supersymmetric EFT in our setting consists of the following things: the exact superpotential, or practically exact, the Kähler potential and the Kähler coordinates at string tree level, so on the sphere, but to all orders in alpha prime. Now, we're not making the claim, and the following claim would be false, that the EFT shown on this slide is the leading description everywhere in the moduli space. That's just not true. What we're going to do is select a region where we think we can find a vacuum, where it will be self-consistently the case that these terms listed are the dominant ones. And then as long as we can find the strength to compute these terms, we can check the vacuum structure. So importantly, and this is one of the main places where we're making a move beyond the blueprints that were laid out in the KKLT paper in 2003. We're not just working at leading order and alpha prime, we're including all order alpha prime corrections. So a series of worldsheet instanton corrections, in fact, to the Kähler potential in a specific sense that I'll describe. So the basic point, though, is that all of this stuff is in principle computable in terms of topological and geometric data. So just to give a face to those things, here's the kind of geometric data I'm talking about: intersection numbers of a Calabi-Yau threefold, intersection numbers of its mirror. So periods, which is to say integrals of the holomorphic 3-0 form over cycles. Threefold. And then the data of quantized fluxes, so how many units of different field strengths are included. And the basic picture is that everything one needs for the leading order EFT is determined by these data. So if we can figure out how to compute these data, we can write down EFTs and then see whether those EFTs have de Sitter vacua. And that's what we've done. We computed the leading order EFTs in 200 million compactifications, and then we found de Sitter minima in some of those theories. Okay, so I think it's important to understand why this work is happening now. The Calabi-Yau threefold examples that you can get your hands on with pencil and paper are just too limited, in my opinion, to realize KKLT de Sitter vacua. And the reason is that the fluxes in the topology are the discrete dials. This is what we learned from Busso and Polchinski in particular. To try to adjust in a rich landscape, one needs to have a high dimensional moduli space, a lot of discrete configurations. So you need many moduli, and once you need many moduli, you can't handle the computation with pencil and paper anymore. Now, it's the case that computational geometry of Calabi-Yau threefolds has advanced enough so that many moduli cases, and hence de Sitter, are in reach. And it's not actually due to AI or Moore's law, just development of methods adapted to the problem. So we are certainly thinking about how, for example, AI could help in next generations of this work, but everything so far has simply involved developing appropriate algorithms in a traditional manner. So what we've done is built technology to compute 4D EFTs and find minima of the moduli potential. And we put all those capabilities in a publicly available software package, CY Tools. So maybe just one piece about, let me remark, this is not something that we've built only to find KKLT vacua. We built this to understand the whole landscape of at least type 2 flux compactifications and F-theory compactifications, and eventually more besides. But in particular, we can apply it to KKLT. So a bit about the setting where we do this. We're working with Calabi-Yau threefold hypersurfaces, i.e. the Calabi-Yau threefold is defined as a subvariety of complex codimension 1 in some four complex dimensional ambient space. We're working with mirror pairs of Calabi-Yau threefold hypersurfaces, X and X tilde, in pairs of 4D toric varieties, V and V tilde, that are defined via triangulations of four-dimensional polytopes. So I won't go through the machinery of that, but just as a picture on the left, you see the 16 two-dimensional reflexive polytopes. And Kreutzer and Skarka found that there are 473 million four-dimensional reflexive polytopes. It's that set of 473 million that we'll be dealing with. And if you go and try and find triangulations of those polytopes and associated toric varieties, you find the number of Calabi-Yau threefolds could be exponentially large. So this is a huge search space. This fulfills our criterion of being host to a wide enough variety of possible solutions that we can try to find interesting things. It's also the case that it's combinatorial. By moving around the data of a triangulation, for example, the two squares with different diagonals shown there, by changing the triangulation, you're making a discrete move that can change the associated geometry. This allows you to use combinatorics to navigate rapidly through these solutions. It's much better than straight up algebraic geometry for this purpose. The basic tech that we needed is the ability to do mirror symmetry in practice. So mirror symmetry was laid out a long time ago. And the basic story is that if you can compute the periods, the integrals of the 3-0 form, then you can obtain the prepotential. And from the prepotential, you'll know everything you need about the n=2 theory. And from that, you can make your way down to the n=1 theory. And this was also figured out in principle how to do it for hypersurfaces in the 90s. And with codes available then and built on those ideas, you could access cases with modest numbers of complex structure moduli. This task gets harder as the number of complex structure moduli grows. It gets harder exponentially, and you could get up to maybe 10. Our contribution is really doing this in Calabi-Yau threefold with many moduli. And with CY tools, we can access anything in the Kreuzer-Skarka list, which means anything up to 491 complex structure moduli. So we can work anywhere we want in that realm. And as just a picture, so on the vertical axis, you have H21, the number of complex structure moduli. On the horizontal axis, H11, the number of Kähler moduli. And as you go out along either axis from the origin, the complexity of analyzing either a Calabi-Yau threefold X or its mirror grows exponentially. And so the farther you get from the origin, the harder the compute gets. I've shaded the regions where you could compute GV invariance with prior software packages. But now we can compute GV invariance wherever we like in this whole realm. We've opened it up. And so now we can look for a Vacua there. OK, so that's the end about the strategy and tools. Now we'll talk about mechanism for a small superpotential. Any questions about the sort of computational geometry? OK, small superpotential. So let's think about how to get small vacuum energy in principle. Buso and Polchinski taught us that you could try to make a small cosmological constant by appropriately choosing quantized fluxes in a high-dimensional lattice. So here I pictured a two-dimensional lattice. And the basic idea is you imagine that the vacuum energy is, in this toy model, a large bare negative term minus m Planck to the fourth, say, plus a term that's quadratic in fluxes, those are the vectors q, knit together by some quadratic form, some sort of metric. And then the idea is that if you can choose the q's very well, such that their length is just a little bit above m Planck to the fourth, then you'll get a very small positive cosmological constant. But you can see what that's doing. You're fine-tuning an enormous number of terms to exponential precision. And the first problem with this general approach, not to say that it's not potentially how things actually work, but the problem with actually trying to do it is finding exponentially small cosmological constant is exponentially costly. So concretely, you want to get a cosmological constant of order 10 to the minus n, you typically have to try about 10 to the n different prices of flux. The other problem is that this toy model is a rough schematic. It's not precisely according with the vacuum energy that you would compute in a real solution of string theory. And our approach is a little different. Our mechanism for small vacuum energy is to work in quite low dimensional lattices between dimension 4 and 10. And instead of canceling an exponentially large number of order 1 terms against each other, what we do is we solve a particular Diophantine problem to find vacua in which all the perturbative terms are exactly 0 along one complex direction in the field space. So there's one complex flat direction that's exactly flat, at least exact at the level of the perturbative theory. And there are only non-perturbatively small corrections along that direction. What remain are instanton effects. So if you've cleared out all possible perturbative contributions to the vacuum energy along a particular valley in the moduli space, what remain are only the non-perturbatively small effects there. And what we then do is make discrete and explicit choices of the topology and the quantized fluxes in order to tune the exponents of the instantons to polynomial precision. But if you tune exponents to polynomial precision, you can arrange for a very, very small vacuum energy, as follows. So here's an example drawn from one of our real computations. This is a superpotential as a function of a single complex field tau, which you can think of as the axiodilaton. And what you see is that the superpotential written here is the sum of two exponentials. And those exponentials have very, very close coefficients, but not exactly the same. sorry, the exponents are very, very close, 7/29ths and 7/28ths. And this is what was long ago called a racetrack. And what you can easily check is if you minimize this superpotential, then the result is an exponentially small value. You see in the result for the vacuum energy here, the ratio of the prefactors 2 and 252 appearing as the base. And then the exponent involves the 29, sort of the difference in the exponents. And that number, 2 over 252 to the 2 times 29, is actually 10 to the minus 122. It's small enough to account for the smallness of the observed vacuum energy. Yes, Veronica.
Are you doing this as something that may be actually happening, or are you viewing it more as just a tool for the calculation?
Right, thanks. Is definitely not actually happening quite the way that I've written it, because the configuration that we're describing gives rise to an n equals 1 supersymmetric ADS vacuum with vacuum energy whose magnitude is smaller than the observed vacuum energy in our universe, but it's negative. And moreover, and this is worse, it's not just the negative vacuum energy, but the Compton wavelengths of the moduli are horizon size. Okay, so it's hopeless in a certain way. And so this particular thing, no, this is definitely not happening. However, in my personal opinion, mechanisms for making exponentially small things are quite rare in certain corners of string theory. There's often a question of the form, why doesn't anyone build certain kinds of vacua in heterotic or in M3 or whatever, boils down to nobody has a mechanism in hand for arranging a separation of scales between the string scale and the dynamics scale. And so what could certainly happen in a real solution is that instead of going all the way down to the real vacuum energy scale, you get yourself way, way, way below the string scale or the Planck scale by a mechanism like this. And that's in fact what will happen in our de Sitter vacua toward the end. The de Sitter vacua that I'll quote to you at the end will have vacuum energy plus 10 to the minus 19 m Planck to the 4th. So, still not something you want to manage tuning by perturbative stuff, but of course way bigger than it. Yes.
Hi.
Hi, Raphael.
This is just a small remark on your concern number one. Not really a disagreement, but Ning Bao and Stephen Jordan and Brad Lackey and I showed that there are fast optimization algorithms that actually find vacuum with acceptably small cosmological constant very quickly in sort of toy landscapes like this.
Totally. Yeah, it's a good point. So I would like to discuss at some point in the future. I've never been able to convince myself that those algorithms would also work in slightly less toy landscapes, but it's a perfectly fair point.
Liam, can I?
Please.
Can I ask you just another question? I mean, if these hints that dark energy is actually changing slowly, could having very light moduli of this kind be a feature, not a bug?
Well, I would say that could work out if what one were gifted by this kind of construction happened to be a few light moduli and the rest up high. The problem is the way that I've built this, the gravitino mass is low. And so everything, all splittings and super-multiplets are of order the Hubble scale. And so that is not going to then work for anything. One would need some sort of hybrid version of this where some sector comes down quite low and then maybe you could live with it, but there's high splittings in other places. And that we don't yet have any idea for. And in part for that reason, I want to advertise that although I really think, and also to Veronica's question, I don't know. I'm intrigued by the possibility of a conceivably better way of finding exponentially small vacuum energy. Let me expand on what I mean by better. You can take configurations where the counting due to Denif and Douglas says there's no way that there's very small vacuum energy in such a small moduli space. And with this mechanism, you can easily get 10 to the minus 100. So there are things, this mechanism is revealing things about the tail of the distribution that one can't see in the continuous flux approximation of Denif and Douglas. I am intrigued by the possibility that this mechanism could actually tell us something, but right now it hasn't. Right now it's only given us the building blocks for making semi-realistic realistic de Sitter vacua, but with much, much higher scales. So although I invoked the cosmological constant problem as a vision, it's in the same sense that I invoked I would like to understand quantum gravity and quantum cosmology in our universe as a vision is not in hand. Okay, so just an overall summary of what we've done with supersymmetric vacua. We found solutions of the form ADS4 cross X6. It's actually a warped product, but not importantly warped, with X6 a Calabi-Yau orientifold with three-form flux. And the solutions are supersymmetric. They preserve n equals 1 SUSY and 4D. The vacuum energy is exponentially small, and there's hierarchical scale separation. So the ADS length over the Kaluzic line length can be bigger than 10 to the 100. And the basic mechanism is a racetrack. It's a racetrack of what turn out to be worldsheet instantons in the mirror type 2A compactification. And in the end, the vacuum energy is an exponential in integers that are determined by topological data, Gopuka-Moravasi invariance and flux quanta. And so we can just go out and find one compactification after another until we find the right set of GV invariance and flux quanta to give us the vacuum energy that we're looking for. And again, that's a tuning of integers by discrete choice, by finding a model, find another model until you find one that's right. And you're tuning to polynomial precision in an exponent, mapping that through an exponential to get an exponentially small energy. Okay, so now let's turn to de Sitter vacua, built on this same framework. So KKLT made two profound claims in their 2003 paper. Their first claim is that in type 2b compactifications in which the superpotential from fluxes is exponentially small, there can exist well-controlled supersymmetric vacua. Yes, question.
Hi, Liam. Sorry, I have a question. This might be naive, but I think of the cosmodule constant problem as a problem of having, maybe you have these very small cosmodule constant vacua, but they're just extremely unlikely. So I was wondering if with your method, you can have a rough intuition of what's the ratio between the number of these small cosmodule constant vacua and the number of vacua you're actually searching over.
Yeah, very good. Thank you. So one thing that I skimmed over is that the distribution with this mechanism is d log rho rather than d rho. In other words, the distribution is more or less flat on a log scale in vacuum energy, which is enormously more supportive of finding small vacuum energy than the ordinary d rho that one might have guessed. Okay, so that's a sort of a first point. Then there's also a practical point. I talk about the computations being difficult and searching in these high dimension spaces, et cetera. Well, there was a lot of work required to get the machinery operating. But if you want to go out and just find a Calabi-Yau that has a superpotential such that the vacuum energy would be 10 to the minus 50, you just start the calculation and 30 seconds later, you'll have examples. They're really quite prevalent. You don't need exceptionally rare choices of fluxes. They have to obey conditions, but the conditions are not extraordinary ones. And so that is maybe a surprising and pleasant characteristic of these solutions that everything is measure zero in a finite set. There's also our measure zero, but they're not like an absurdly rare measure zero thing. It's a Diophantine problem, but it's not a Diophantine problem where you almost never find a solution. Does that address the question at all?
Yes, thank you.
Okay, so KKLT made two claims. First claim is that if you can find a compactification with exponentially small flux superpotential, then there can exist, subject to some other conditions you'd better check, well-controlled supersymmetric ADS4 vacua. But then they further said, if that compactification, an ADS4 vacuum, also has a warp-deformed conifold region, i.e. a Klebanov-Strassler throat, and if in that Klebanov-Strassler throat there are one or more anti-D3 branes, then again, in a suitable parameter regime, which one has to check, there can exist, they claim, metastable DS4 vacua. This scenario has been intensely studied over the past 2 decades. And one of the most fundamental questions about it is, do there exist consistent compactifications of string theory realizing this idea? And I claim that our work in 2021 that I was summarizing a few slides ago suffices as a demonstration of the first claim. We gave an explicit construction establishing, at least in my view, that there are supersymmetric ADS4 vacua of KKLT type with exponentially small vacuum energy. And now for the second claim, de Sitter, where, as you might expect, going from a supersymmetric to a non-supersymmetric case, the claims I make will have to be much more guarded. So what's needed? If you compare the first claim and the second claim, to go from ADS to DS, one needs to also have, on top of the ADS vacuum, a Klebanov-Strassler throat, i.e. a warped conifold, and antibranes. So we went looking for that. And here's the scope of the search. We looked through 202,000 polytopes with complex structure moduli dimensions ranging from 3 to 8. We built 240 million flux vacua with conifolds. And of those, 33,371 are flux vacua that have an antibrane, one or more suitable number of antibranes in Klebanov-Strassler throats. In general, it turned out to be one antibrane in each case in the Klebanov-Strassler throat. Now, those aren't de Sitter vacua yet. Those are the preconditions for de Sitter vacua. And now we have to try and ask, when all the moduli are stabilized, is the result de Sitter or a runaway? It turns out that in the configurations that we were looking at, the number of moduli was at least of order 100. 100 complex fields, so 200 real fields. And an unguided search in that space is completely hopeless, especially once you look at the shape of the potential. You realize that the basin that holds the KKLT minimum does not have a really wide attractor around it. So you'll have to start very close if you're going to find it by any means whatsoever. And so in 100 dimensions, that's hopeless. And what we did is we used a series of more and more precise analytic and supersymmetric starting guesses to narrow in the numerical search to an appropriate place. So in the complex structure sector, what we did is solve the Diophantine equation I described before to find a single flat direction that along which the perturbative terms vanish. Is what we call a PFV, perturbatively flat vacuum. That's a particular one field effective field theory. And what we do is use that one field EFT to find a good guess to where the solution will arise in the full theory. Then we go back and check in the full theory and see if we can recover it. So it's a means of clever guessing. And in this way, we engineer a small flux superpotential and we engineer a Klebanov-Strassler throat. And we were successful at doing this. Now, turning to the Kähler moduli sector, we first find a supersymmetric ADS vacuum and use that as a starting guess to find a de Sitter vacuum in the full theory. So let me show you a picture of this. This is a cross-section of a particular representation of the Kähler moduli space in a threefold with 491 Kähler moduli. What you're looking at is a collection of phases. Each little polygon is a phase, and from one phase to another, you're going through a flop. Some kind of curve is flopping, and the geometry in general is changing. This is described by 491 parameters in this case. And you imagine you start at some place in here and you'd like to find a supersymmetric vacuum. And maybe the supersymmetric vacuum lives over on the other side. So what you have to first do is navigate your way through all of these phases, find your way to the vacuum. One can do that. We've prepared algorithms that succeed at doing this relatively quickly, in fact, despite the scope of the task. Once you've done that, now let's zoom in on the supersymmetric vacuum. And what can be the case is that the de Sitter vacuum is quite nearby. After all, adding the antibrane shifts the VEVs of the moduli by only a small amount. So then we use the supersymmetric one as a starting guess and essentially do Newton's method in that vicinity and navigate our way to the de Sitter vacuum. In this way, we've found 30 KKLT de Sitter vacuum. Coming back to the question of rarity of these things, while I wish they were more common, this is not that absurdly rare, really, given the number of constraints that we're imposing. So let's look at an example so we can get a sense of how good or bad these things are. So there's a particular Calabi-Yau threefold hypersurface with 8 complex structure moduli and 150 Kähler moduli, where if you pick these fluxes, so M are the fluxes of F3 and K are the fluxes of H3, the RR and NS three forms respectively, if you pick them to be these lists of integers, then one finds that the compactification contains a Klebanov-Strassler throat that hosts a single anti-D3 brane. And if you include the supersymmetry-breaking anti-D3 brane potential, computed at leading order in G string and alpha prime, as in the classic works of Kachru, Linde, and Kachru, Kallosh, Linde, and Trivedi. Then if you do that, if you include the anti-D3 brane potential at leading order in alpha prime, you find at this level a de Sitter vacuum with these parameters. So M here is the D5 brane charge dissolved in the Klebanov-Strassler throat. It's the integral of F3 over the A cycle at the tip of the KS throat. G string M is a parameter telling you how weakly curved the throat is. When G string M is big, the throat is weakly curved. G string is the string coupling. W naught is the flux superpotential. When it's small, the vacuum energy is small. And V0 is simply the actual four-dimensional vacuum energy in Planck units. And you see that it's comfortably below the Planck scale, and it's positive. So here's what this geometry's potential looks like. As in the beginning of the talk, vertical axis is the vacuum energy, horizontal axis is the overall Calabi-Yau volume in string units. And you see that as drawn in pink, the de Sitter curve has a minimum at positive energy. So how happy should we be about these parameters that I've presented? So let's examine them and think about it. First of all, G string is really small. 0.06 is much smaller than the values that one often has to deal with in any kind of realistic construction. After all, in the standard model, we deal with loop counting parameters that are order a third without much trouble. So this is comfortably small. We expect control of the string loop expansion. Of course, because I can't compute to high order in the string loop expansion, I can't prove to you that it's under good control, but I really don't lose any sleep about that. The vacuum energy is small compared to M Planck, so there's a comfortable hierarchy of scales. That's nice. W naught is small, but it's not exceedingly small. And so for this reason, it's important that we didn't just work to leading order in W naught, we worked in the full theory of the complex structure module. I haven't shown you any of those details, but that's what we in fact did. So the size of W naught is also not a limitation of our construction. On the other hand, G string M is not large. And that means that the analysis that Kachru, Pearson, and Verlinde did, in which they showed that a suitable number of anti-D3 branes in a suitably big Klebanov-Strassler throat gives rise to a supersymmetry-breaking metastable state of the gauge theory. That metastability analysis is not a priori applicable. So if I make up an error budget here, the error we make in the superpotential is totally negligible. We computed it explicitly, and they're really tiny truncation errors. The error from alpha prime corrections to the Kähler potential, well, we actually include series of worldsheet instanton corrections to the Kähler potential explicitly. So we just have small truncation errors there. String loop corrections to the Kähler potential, we can't compute. So they're in principle not known, but naive dimensional analysis plus the value of G string tells us that they ought to be under control. Nevertheless, that's not as good as the other pieces further to left in the error budget. And then finally, the study of the anti-brane at leading order in alpha prime is really an expansion in a parameter of order 1, so we shouldn't trust it particularly far. And it's particularly for this reason that we call our configurations candidate vacua. So just to recap, the metastability analysis of KPV, which tells you that under certain circumstances an anti-brane breaks SUSY metastably, is not directly applicable in our setting. And further work that has examined alpha prime corrections there is still not yet applicable in our setting. And so what's needed is to understand the criteria for metastability at G string M of order 1 to determine whether our compactifications really furnish de Sitter vacua. So to my mind, the main reason for the modifier candidate is this, not any of the other potential risks. So where can this go? How can one do better? Well, the space of vacua is extremely large, and this was, after all, our first paper on trying to find de Sitter vacua in this space. We're working energetically on it now. One can improve the search methods by a great deal to find examples that have all the control parameters better. Smaller superpotential, smaller string coupling, less curvature, larger G string. In parallel, one can understand the theory a lot better. One could try to understand string loop and alpha prime corrections to the Kähler potential. One can try to understand Pfaffian corrections to the superpotential. And one can dig in and study alpha prime corrections to the anti-D3 brane action. So this is, I think, very important area for future work, not just for this construction, but for all kinds of related attempts to build realistic vacua. I should say, I forgot to mention, and this is perhaps relevant for a quantum cosmology series, these are not in any way classical solutions. Quantum effects, four-dimensional quantum effects from instantons and strong gauge dynamics in the infrared are crucial for the vacuum energy, for the vacuum structure here. And that is a relatively special feature of KKLT constructions and related constructions like the large volume scenario. On the other hand, I certainly think that any attempt to give compelling evidence for a de Sitter vacuum in string theory is going to run up against some sort of task like what's shown here, some set of cases where one needs to compute to higher and higher order in various expansions to understand the theory better. I mean, we tend to forget if we live too much in more supersymmetric realms, but there's relatively little that we can do beyond leading order or first perturbative order in the two fundamental expansions in string theory. And once you start dealing with non-supersymmetric vacua, that problem comes home. Nonetheless, one can try, and we're trying. So let me sort of wrap up and then we can discuss. So I've described our program of computational compactifications, and I've shown how for type 2b on Calabi-Yau threefolds and toric varieties, we can, in practice, at scale, compute the topology of threefolds and their mirrors, find the superpotential that comes from fluxes and Euclidean D-branes, solve a particular Diophantine problem in the quantized fluxes to find a 1D effective theory, and select cases where competing exponentials along that one direction give a vacuum with exponentially small vacuum energy. In this way, we've constructed n equals 1 supersymmetric ADS4 vacua with all moduli explicitly stabilized. And these solutions feature exponentially small cosmological constants and giant scale separation. And in this way, we're building a corner of the landscape in enough detail that we can not only try to search for de Sitter vacua of string theory, but we can reasonably expect that we'll eventually succeed. So concretely, we've constructed in this setting candidate KKLT de Sitter vacua. We gave the first examples of Klebanov-Strassler throats in stabilized Calabi-Yau threefolds. We gave the first examples of anti-D3 brane uplifts to de Sitter. Now, so far, what I've told you only holds at leading order in the alpha prime corrections to the anti-brane action, but that, after all, was the approximation of the classic works on this subject. And so, at least at that level, we've succeeded in some way, and one would like to do better and work to higher order. So we're searching very hard for vacua that can more manifestly survive alpha prime corrections. And overall, I would say there are bright prospects for systematic construction of de Sitter vacua in compactifications on Calabi-Yau threefolds. Thanks a lot.
Okay, so thanks for the talk and leaving us lots of time for questions. Maybe I'll start with a question.
Hundreds of backup slides with details if people want to know any details. Please go ahead. Sorry.
Yeah. So I just wanted to make sure with these scale-separated supersymmetric ADS vacua. So there, you would say everything is really under control, or I mean, are there any doubts in that set of examples?
Yeah, good. So what's most worrisome in that case? So what do you need to do? You need to be sure that you understand the n equals 1 theory. So the n equals 1 theory consists of a superpotential and a Kähler potential. The superpotential we've explicitly computed. The flux superpotential comes from doing period integrals, which we've done. And I can show you in as much, one can show excruciating detail that demonstrates that we have that under perfect control. And so we could calculate to higher and higher order in the worldsheet instanton series of the 2A mirror, and that's perfect, no problem. The other terms in the superpotential come from Euclidean D3 branes. We know and can directly compute which Euclidean D3 branes have the right number of zero modes to support superpotential terms. And we know the semi-classical action. There's a Pfaffian prefactor. And the Pfaffian prefactor, in principle, in many cases can depend on moduli. We worked extra hard to find cases in which there can't be any moduli dependence, at least in the absence of mobile D3 branes. So in other words, the Pfaffian is a section of a trivial bundle over some other moduli space. And work by Manki Kim, who's in the audience now, and others, has advanced the understanding of what constant value the Pfaffians take. But in our recent work, we marginalized over this unknown by taking the Pfaffians between 10 to the minus 5 and 10 to the 5. And it's just a fluctuation determinant, so it should be like order 1 or 10 or something. And nothing changed in that range. So I really am not worried about those either. Bottom line, superpotential is solid. Now with the Kähler potential. One thing that's a little unusual about our constructions, and in a 2-hour version of this talk, I would tell you in much more detail, is that at our vacuum points, some curves are small. And at first sight, you would panic and say, small curves mean you don't know the alpha prime expansion at all. But you can just check. All the small curves are flop curves. And you do understand what happens near a flop. In particular, you understand what happens near a flop if the integral of B is a half as you go toward the flop, because then you sort of avoid the singular point. And so the overall picture there is at the level of the Kähler potential that's inherited from the pre-potential. Sorry, at the level of the Kähler potential that's inherited from the associated n equals 2 model. Okay, this is on the hypermultiplet side, but still. We have, I think, perfect control. By perfect, what I mean is we can compute as far out as you want, and I see no reason to be worried about anything. What would you be worried about? The biggest worry, if I had to complain about something, I would say, look, there could be an n equals 1, but not n equals 2 string loop correction to the Kähler potential that depends on moduli. We worried a lot about that. We wrote a lot about that. It would have to be quite exotic, because we can follow through lots of transitions associated with loci where such curves can get small. And what would have to happen is that these corrections would have to display discontinuous behavior as one goes from the G string equals 0 theory to finite G string. They would have to move sort of some things infinite distances in moduli space. And it just doesn't seem plausible that that will happen. But since I can't compute these, I can't be sure. What we did in the de Sitter paper is give very detailed estimates of what we thought were the most dangerous curves. And we explained what we thought those corrections were, and they were percent level corrections. Now, another piece of the error budget, which is significant, is warping. So we didn't explicitly include warping corrections in everything, only in the anti-brane energy. But warping actually affects some of the Euclidean brane actions. And without a metric on the whole threefold, which currently you can't get at these Hodge numbers, when H11 is large, it's a hard compute. In fact, it's an infeasible compute. We weren't able to check that directly. We made estimates. The estimates these are sort of 10% effects. So those are in principle worrisome. They're not 10% effects in the SUSY ADS vacuum. In the SUSY ADS vacuum, it's much better. And so my final answer for the SUSY ADS vacuum is the particular ones that we described might conceivably have some error, but I really have not been able to think of what that could be.
Okay, great. Thank you. So Berkeley has a question.
Hey, thanks for the beautiful talk and these very impressive results. I'm trying to understand a little bit more the philosophy, maybe to sort of give my perspective. I never thought it was going to be obvious that we, eventually should be able to find an explicit solution that is a metastable de Sitter vacuum in string theory any more than, we're able to find explicit solutions for a plutonium nucleus in the standard model. Some things are just very messy and complicated, and just because we don't have an explicit solution doesn't mean that we believe that a plutonium nucleus can't be accounted for in the standard model, or somehow contradicted, or standard model is false. So with that perspective, would you say that this is an attempt to sort of find a sort of in principle proof that such vacua exist rather than phenomenologically motivated ones? And how does that relate to sort of this distribution of the cosmological constant, the answer to Stefano's question, where, if it actually were distributed in that way, then, after breaking supersymmetry in a way that accounts for the standard model, you'd have to solve the cosmological constant problem all over again.
Yeah, right. Absolutely, right. And so my personal goal is not to provide something along the lines of a proof, in part because, in a complicated physics problem like this, whether something is a correct proof or not depends on the observer in many ways. And so I don't think that that's entirely productive. What I would like to be able to understand is better toy models. So let me give you a complete fantasy of what you might want to do with something like this. If you had your hands on examples of these that you really trusted, and then in some futuristic world, you could find the CFTs and understand them, then you would have a completely different way of accessing information about a de Sitter configuration. So that's like the kind of thing you might get. Another thing you might kind of get is much more phenomenological, which is to try to understand if this is the mechanism at work, then what would that tell you about the characteristic properties of the moduli of So what would that tell you about whether this works when the number of fields is stupefyingly big, as in certain of these F-theory models, or does it only work in models with small numbers of moduli? Those kinds of things. I don't think it's to answer an existence question.
Okay, Andre?
I have a question, not exactly on the whole construction which you are making right now, which is very interesting. But my question kind of, did we miss anything in the possibilities in the setting? Because like 5 years ago, I started just looked again at KKLT as it was with exactly the Keller and superpotential, etc. And I found the following, that if you do it conventional way, then you find out anti-de Sitter minima if you have the two parameters W0 and A. So only if W0 is smaller than A, then you have a supersymmetric ideas. But what I have found that if you look for solutions with W0 larger than A, which was unusual, then you, of course, do not easily find any ADS. However, it's very easy to find a stable, metastable, de Sitter solution directly. And maybe this range of parameters, W0 larger than A, are phenomenologically or theoretically not trustable, whatever. I just wanted to say that this possibility, I don't think that anybody, or at least to my knowledge, studied it. So the question is whether it is unfeasible or just nobody realized that KKLT has different solution.
Yeah, so it's not that's not a regime that we've carefully studied. I will say one remark in accord with what you're saying is that the sort of general perception after the original KKLT paper, at least as I perceived it, was that the only way this was ever going to work is if W naught is really, really small, and maybe one can't get such small values. And that's just not true at all. I mean, as you've expressed from a different line. But the example that I showed in this talk of a de Sitter candidate has W naught 0.01, but in fact, there are other examples that we've studied where W naught can be really quite close to 1, and as long as you know what you're doing in checking carefully the complex structure stabilization, there's no problem whatsoever. The basic reason being that there are other factors at play in ensuring that the alpha prime expansion is under control. So I do agree, generally speaking, that it's not the case that ultra small W naught is the only way. We exhibited ultra small W naught examples just to show that that was possible. So coming back to Raphael's question, for ridiculously small vacuum energy, I did feel that there it was useful to show that there wasn't some sort of conjectural obstruction to finding extremely small vacuum energy. We could just have one, look at it and say, no, this definitely is fine. Of course, doing that for de Sitter runs into the problem of the actual CC problem, which again, we're not tackling.
Yeah. Just returning to my question for a second. So my main concern was whether this not liking the possibility that W0 is larger than A goes back to, since we have found ADS, then what do we need? ADS, supersymmetric, everything is great. So the idea that you go directly to non-supersymmetric DS solution, maybe it is not attractive, but I just wonder whether anybody really studied this point, because just from the point of view of explicit KKLT, the solution was missed. It exists.
Yeah, no, I definitely take your point, and I think that one of the issues with these kinds of constructions is that, as you know very well, once one has the right idea, doing the analysis for the EFT is, the work of one serious paper or something like that. But the work required to really set up machinery to study a slightly new parameter space can be harder. What I haven't checked in our case, whether the tools that we've developed could be easily repurposed to that regime. I suspect they could. I would certainly be worried about control of the alpha prime expansion in the regime you're describing, but without really looking into it, I can't tell. But yeah, I do think that you're right that it hasn't been investigated in depth by other groups.
Steve, go ahead.
Yeah, thanks. I wanted to ask a bit more about the comment you made about thinking about these anti-de Sitter vacua as CFTs. Where do you anticipate, will there be some new insights from thinking about it that way? I mean, is it possible to take the data from one of your ADS solutions and stick it into a bootstrap algorithm and, try to show that it, is at the edge of some island or something?
I'm not going to be the most successful person to try to answer that question. What I can say is that when I have struggled with it and asked people who know better, I haven't heard any good ideas for something that can be done in the near future.
Mm-hmm.
But not done in the near future is maybe different from in principle impossible. And so I do think it'd be worthwhile to poke at it. We have the data. The problem is that the data that we have comes from our calculation from a string compactification of a supergravity theory. And then I don't see how one would be able to use, for example, some bootstrap constraints on that, in principle, self-consistent supergravity theory to learn something. But what you might, in the fullness of time, you might like to actually find a brain configuration that gives rise to something like this, and then you're really learning something. These are all very distant fantasies, but I think they're not more distant than, for example, trying to solve the CC problem, and perhaps in the spirit of the remark I made at the beginning, building fully realized toy models of quantum gravity, of cosmology and quantum gravity. What would you do if you had one of these things? You could ask about couplings in various sectors or something, but you could also try and figure out how do you calculate scattering amplitudes in such a vacuum, or is there a holographic description of any kind?
Yeah. Okay. I mean, I was thinking maybe to get information about more of the excited states to feed into the bootstrap. You say it's kind of impractical to compute the Calabi-Yau metric in these situations, but you might try to compute, I don't know, a bunch of non-protected scaling dimensions or something like that.
Yeah, so the trouble, I would say, at least in these most gapped models, is that the low-lying spectrum is, let's say, about 300 moduli fields.
Mm-hmm.
And then, hierarchy of 10 to the 20 before you get to the KK scale or something like that.
But I mean, if you could get the moduli on the Calabi-Yau, if you get the metric on the Calabi-Yau, you could probably get some of those other dimensions by solving some Laplace's equation or something.
Yes, coming from the point of view of someone who's never tried these calculations, my impression was that if the gap in dimensions was gigantic, then you were going to be hard pressed. And that is sort of a key feature of these. So if you solve Laplace on these Calabi-Yaus, you're going to get KK modes of something. And the problem is those KK modes are going to be up, examples we looked at, they'll be at, let's say, 10 to the 16 GeV or something like that. And then the moduli masses are vastly below. So, yeah, what you're describing is certainly in the spirit of what I would hope for, but I have yet to find a lot.
I don't see why the gap is, makes it out of control. It seems like the problem is just getting a good approximation to the Calabi-Yau metric.
So you say it would be enough to know about the low-lying spectrum, and then to say percent precision the high up spectrum or something.
Well, that would at least be a start. Then you stick that into a bootstrap and maybe try to refine it or something. You might need stringy towers, and that would involve, I mean, I'm not sure what's required, but I think, if you knew the Calabi-Yau metric on your models, which is a challenge, I mean, but I don't know how big a challenge. Maybe when you ask people that think about computing Calabi-Yau metrics on a complicated threefold like this, how bad a problem is it?
Nobody has offered me a scaling behavior as a function of H11. What people tell me is they can do H11 of like 4 or maybe 5 at present. And in past years, they could only do the quintic. But I really would like to see like a determined scaling analysis of this problem, because the best model that I've presented, at least the smallest H11 model that I've found in the work reported here, has H11 of 93. And so that's still a ways off. On the other hand, it's probably an easier problem than the bootstrap problem that we're talking about.
Yeah. Okay. All right. That would be an interesting thing to know. Okay. Thanks.
Can I make a comment about the metric? Actually, Liam, I think the problem might be much more simpler than what you presented, because of the mirror symmetry, of course, there's going to be some N1 corrections, but if you discard the N1 corrections at the level of N2 data, mirror symmetry tells us that if you have 93, 97 moduli in the Keller moduli sector and then 4 moduli in the complex structure, then you can just flip the game and then look at the mirror Calabi-Yau, where the number of Keller moduli is 4 and the number of complex structure moduli is, say, 97. If you do so, then just fixing a point in the complex structure moduli space and then computing the metric becomes more feasible, much more easier than what you originally described. And then just computing some spectrum there will eventually agree with the original Calabi-Yau. So I think it's a much better situation.
That's fantastic. That's an excellent point. Of course, I mean, as you mentioned with the N equals 1, once one eventually has to put in warping and the like, it'll get complicated, but that's still quite a boost.
Liam, to the extent that you have control either in the ADS case or the de Sitter case, can you say how light are the lightest scalars in these effective theories?
Yeah, their masses are of order the gravitino mass. And so the gravitino mass is set by W with an e to the k over 2 in front of it. And so in the case of the ADS, where the vacuum energy is the present day vacuum energy, the masses are the Hubble scale.
Okay.
Very roughly. So there are a bunch of polynomial prefactors that one needs to account for, but roughly speaking, that's what's happening, and that sort of makes sense. M3 half squared m Planck squared is your vacuum energy, and so you get 10 to the minus 3 electron volts to the fourth from 10 to the minus 33 electron volt masses. Does that address the question?
Yeah, that's
so that means that in the de Sitter case, because the vacuum energy was 10 to the minus 19 in Planck units, well, the mass splitting, the masses are quite sizable still.
Okay. Great. Any other questions?
Let me just briefly make a comment, which is that I know at least one group is working on computing numerical warped Calabi-Yau metrics. I don't know what they've found so far because I'm not on the collaboration that's doing it, but I know that it's in progress and they seem optimistic that it will be coming out soon-ish.
Yeah, so that it's good that you brought that up, Richard. So one thing that I forgot to mention in the overall sort of summary of could there be anything wrong with these models? I mentioned that warping gave sort of 10% corrections, but there's a general concern that in certain of these de Sitter constructions is what's called the singular bulk problem, which is basically a relationship between the tunings needed to arrive at the correct vacuum energy and the appropriately warped throat and the profile of the warp factor. And it's entirely possible, I think it's actually sort of relatively likely, that the first results that come out in finding warped metrics will look quite dangerous for these particular constructions. And I just wanted to remark that our experience in adding layer after layer of corrections, so worldsheet instantons, more worldsheet instantons, perturbative corrections, et cetera, is as we did that, very often a choice of fluxes or a point in moduli space that gave rise to a vacuum would no longer work, but there would be a nearby one that did work. And so there's a lot of moving around in the space of possible vacua. And each new shock of a new correction will probably wipe out a previous generation of proposed candidates, and their neighbors with small adjustments in fluxes and vevs will then be the ones that are appropriate. I mean, very concretely, in some of the models that I reported, you can find neighbor configurations that are just barely ADS or just barely runaways. And if the vevs were just a little different, why they would have been de Sitters. And so I do think that in the coming years, as we understand more and more corrections, for example, from explicit metrics, we'll probably find that these candidates have to be updated and replaced with other candidates, but sort of in a way that zeroes in on something that's more trustworthy as time goes on. Question from Berkeley?
Just a quick comment on that. I mean, again, for viable cosmology, in the sense that we have a hot Big Bang, it's actually very important that the neighbors have completely different cosmological constants from our vacuum. So I think that's a nice example of where that's a little bit in tension with controllability.
So importantly, I didn't mean that they were neighbors in the field space. I meant only that they were neighbors in the discrete parameter space. So the wall in between could be a sizable change.
Okay, thanks.
Yeah.
Okay, well, if there are no other questions, let's thank Liam again.